Hello everyone, welcome to tutorial on RC coupled amplifier. I'm Arvind and I'm an electrical engineering student, and I would like to help you guys get some understanding of the working of RC coupled amplifier. So let me get right into it. First of all, what is an amplifier? An amplifier is a circuit that helps to amplify or increase the magnitude of the input and get an increased or amplified waveform at the output. Okay, definition solver. So how do we get an amplified output? See, after all, if we think of it only in the most simple sense, when we use a transistor, we know that the input current is IB and output current is IC, and the IC is related to input current as beta times IB, and this beta for the common transistors will be about 100 or 500 range. So actually we can see that the output current becomes more than 100 times the input current, and thus we get an amplified output. But the output power equals the input power. There is no energy creation. What amplifier does is just converts the DC power that is provided to the RC coupled amplifier, and it produces or superimposes this DC power with the AC power input, and this is how we get an amplified output. Okay, so as I said, we could produce this effect only using a transistor, but why are all these elements present here? There are resistors, capacitors. Yeah, why are they present? See, in the broad sense, there are other factors we need to consider. In a transistor circuit, there is something known as the operating point, and it is essential to keep the operating point stabilized, and that is why we study different biasing stabilization circuits, and like the voltage divided bias used here. This helps us to ensure that the operating point remains in the center of the active region, and hence we get a fully amplified wave at the output. Okay, that's done. So I have explained why we use the voltage divider bias here. This is the voltage divider bias actually, and it was used here to stabilize the operating point against other external factors like temperature and change in transistor parameters. Okay, that's done. But why are the capacitors present? Capacitors. Okay. These two capacitors, C in and C out, these are known as the coupling capacitors. The input coupling capacitor, C in, actually what it does is it only allows AC input to reach the base of the transistor, and it blocks any DC component that is present in the input. So actually we only need to amplify the signal. We do not have to amplify some noise that might be present as DC in the input. Also, if we allow the DC to enter inside, it might affect the biasing of the interior part where voltage divider biasing is used. So it is extremely important that any other unknown DC doesn't get inside. Also, this DC that we supply as VCC should not go outside or get divided outside this region. This VCC is only provided to stabilize this voltage divider bias, and we cannot use or divide it further. This VCC is fully required here. So this coupling capacitors, their main purpose is that they provide isolation of this DC both from input and both from output, and the DC is contained here. Also, the coupling capacitors only allows AC to pass, so only the signal gets inside and only the amplified signal, that is AC, gets to reach the outside. Here the load is here, so the outside it will only reach the load as AC, no DC is present. Okay, so I told you about the coupling capacitors just now. Now what? This is an input series resistor that may or may not be shown. It shows the input impedance. Okay, that's done. Whoa, there's one more. The CE. This capacitor, CE. It is known as the bypass capacitor. Why is it called so? You see, when the current flows, there should be a current IE. And if this IE was allowed to flow through the resistor as I am showing now, it would have produced a significant drop. This drop will actually reduce the VBE voltage. You see, the VCC given is a constant, so if this drop is gonna increase, this should decrease to keep VCC constant. So when the input VB base voltage is reduced, the output gain will also get affected and will not get proper amplification, and this unwanted drop in the resistor should be avoided. So when we connect a capacitor like this, it provides a simple, easy path for the current to flow and reach the output load. And that is why it is known as the bypass capacitor. It provides a bypass, that's a path that doesn't flow through the resistor, and it helps the output reach the load. See, for AC, the capacitor acts as a short circuit, and the current always favors the lowest resistance path, and that is why this provides a it provides a short circuit path. So it is an easy path for current, and that is why the CE path is favored, and that is done. So just now I have explained to you all the basic parts of the RC coupled amplifier, and I have also explained how it should work, because the IC is beta times IB, and beta being 100 times, we get an amplified output waveform, and the DC power from the VCC is used to help us get this amplification in power. Okay, now that's done. What we need to look now is only the bandwidth, and it is important. Whenever we speak about amplifiers, we should speak about the bandwidth. So let's go to the bandwidth, and what is it? I'll explain to you. This is the circuit. This is not the circuit, and this is the graph that shows the bandwidth. What is bandwidth? Okay, you see, the bandwidth of any circuit basically shows us that the frequencies is a plot of frequencies with gain. On y-axis there is gain in decibels, and on x-axis there is frequency in hertz. So we just analyze how the gain varies with frequency. Simple, right? We just look at how the gain is going to vary with the frequency, and we just make a plot. And for an RC coupled amplifier, when we make such a plot, we get a waveform as shown here, and this is what we show as the bandwidth, and I will show you exactly what is bandwidth in this diagram. Before that, let's look at why this waveform is produced. So you see, look at this region and this region. In both this region, we see that the gain is lesser, or it becomes reduced when gain becomes reduced when frequency is less than FL, this frequency, and for another frequency FH, the gain gets reduced again. But at the center, the gain is almost constant. So what happens in these two regions? Why is the gain reducing? It's shown here itself. See, at low frequencies, you know that formula of capacitance is given by 1 by 2 pi Fc. So at low frequency, the frequency is reduced, the denominator is becoming lesser, so the effective reactance is actually increasing. That means look at the circuit. Here, here, here. All these capacitors, their reactance is increasing. So instead of acting as a short circuit for the input, and here also we need a short circuit, but now it's acting as a resistive element that produces some resistance here. There's reactance, the word is reactance. So this reactance produces some drop. So a part of the input gets dropped here, part of it gets dropped here, and also the CE doesn't provide sufficient bypassing action. So this causes the gain to reduce, and this is why gain reduces at low frequencies. Understood? So that is how I explained about gain reduces at low frequencies. What about high frequencies? See, at high frequencies, there is some other factor known as the inter-electrode capacitances. Inter-electrode capacitance, what is that? See, look at this. This is a conducting path. This is another conducting path. Or we could say this is conductor, this is a conductor. Okay? This is air. Conductor, air, conductor. Sounds familiar? Exactly. This is a capacitor. Even though it may not look obvious, there's an inter-electrode capacitance that can be formed in 3 junctions like this. Here there can be an inter-electrode capacitance, here also inter-electrode, here also inter-electrode. But we didn't speak about this inter-electrode capacitance before. But why am I speaking of now? See, the inter-electrode capacitance is not a big factor to be considered. It is almost always neglected. But at high frequencies, this needs to be considered. Okay? So at high frequencies, this needs to be concerned. We need to be concerned about this. So at high frequencies, the effect of the inter-electrode capacitance produces a capacitor here, a capacitor here, a capacitor here. And out of all these capacitance, this capacitor is shown to have more effect than the other capacitance. We need not go into much details, but this capacitor produces more capacitive effect than other inter-electrode capacitances. So what if I kept a capacitor here? See, if I had kept a capacitance here, the output might have got a short circuit path to return to the input. I am finding it difficult. I hope you can understand. From the collector, there will be capacitor here, and it will reach back to the base like this. Okay. So this feedback, that is called negative feedback. A part of the output is fed back to the input, and this will actually reduce the gain. Do you know why it can? And why is it negative feedback? See, we are using common emitter configuration. In a common emitter configuration, the output is out of phase with the input. And as a result, a 180-degree phase shift of output is fed back to the input. And thus, the output actually produces negative feedback on the input. And thus, the output gain is reduced. Sounds interesting? Okay, so that's about the interelectrode capacitance. Another factor that we consider at high frequencies is the shunting effect. You see, at higher frequencies, these capacitors act as short circuit, no problem. But this short circuit action is very much high that we can see that the next stage resistors will come in parallel with these two resistors, and this shunting effect can actually reduce the gain. I'll repeat again. At high frequencies, there will be these resistors will come in parallel to these resistors in the next stage. These two resistors will come in parallel with these two resistors in the next stage, and this shunting effect that is coming in parallel of one stage resistors to another stage actually reduces the gain. So I'll not go into much details. It's just enough you use the word shunting effect when you speak at high frequencies. This shunting effect actually reduces the gain. Okay, I hope you understood that. Now, this done. What's here? See, at this region between FL and FH, these effects almost cancel each other. I mean, there is not very much low frequency, or there is not very much high frequency, such that we can get practically a constant gain between these two frequencies. Above this frequency, the effects of interelectrode capacitance shunting effect becomes considerable. Below this frequency, the effect of this reactance of the capacitors becomes considerable. We need to consider them. But at between these two frequencies, it's fine. It produces almost a constant gain. And this region hence is very important to us. It is this region that we use to make the amplifier work. We only use this region for the amplifier to work, and thus this region we just spoke about is known as the bandwidth. So mathematically, what will we give as the bandwidth? There is a upper frequency FH, there is a lower frequency FL. So FH minus FL, this difference or this range of frequency we get is known as the bandwidth. So just now you will understand why we say that when we have large bandwidth, it is good, it is better. Why? Because when the bandwidth increases, we are getting more range of frequencies over which we can use this amplifier, and it is very useful. Bigger the bandwidth, we can use it for more frequencies and get almost a constant gain. Okay, so that's how we explain how the RC coupled amplifiers bandwidth is obtained. I hope you got some idea about how this bandwidth occurs, and I hope you didn't get confused, because this is actually my first lecture on YouTube, and I'm an amateur, and I hope this could help you in some way to get an idea about RC coupled amplifier. The RC coupled amplifier, as I told in the beginning, is not much a very complicated circuit. It could have been done only with a transistor, but we only added these components because we need to bias, stabilization, and also isolation. Only those purposes. That is why we just added these components. We could have got an amplified output with the transistor itself. So it's not much great deal. It's a simple circuit. I have seen people getting more confused about this simple circuit, and that's why I thought of beginning with this circuit in my lecture series. And so this is the gain diagram. Again, the bandwidth diagram. Gain falls at low frequencies, high frequencies. At the mid frequencies, the gain is always constant. So I hope I can rewind and stop this tutorial now. Thanks for listening. Please subscribe and do comment if you have any suggestions. Thank you.